Okay, so today we're going to be talking about imaginary numbers and complex numbers, conjugates, rationalizing the denominator. I think the big thing is that some equations do not have real solutions that make them true. Okay, and so if you look at this equation here, there's nothing you could do to find a real answer that makes it true. And even if you graphed it, it doesn't intersect the x-axis. And so the question is, is there a solution that makes it true? And the answer is yes. If you go into the world of imaginary numbers, you're like, well, why would you want to? Well, we want to keep trucking and say, can we find things that make it true? And so we have talked about, if you cannot take the square root of a negative number, well, can we just like, or very similar to, say you've got the square root of, say, 36, that's going to be 6. We don't and cannot take the square root of negative 36, right? And so like, well, what do? What times itself makes negative 36? Well, 6 times 6 doesn't make 36. Negative 6 times negative 6 doesn't make 36 as well, negative 36 as well. So what do? So just like if you've got like the square root of 20, you can break it into the square root of 4 and 5, where you can take the square root of 4, which is 2, and square root of 5 is just square root of 5. So you write it as 2 times the square root of 5. So because that's true, we also, in a similar fashion, we can say, well, let's put aside that negative square rooted and say, let's call this the square root of 36 times the square root of negative 1. And then that would become 6, and the square root of negative 1 is just the square root of negative 1. And it's so common, just like pi is so common, we call it pi, but it represents 3.14. We use I to represent the square root of negative 1. And so because it's so common. So it's not just a variable that changes values, it's a specific letter to represent a specific item. Okay, and so that is our imaginary unit, which would be I. Okay, and so if it has an I in it, we call it an imaginary number. If it's made up of an imaginary number and a real number, so sometimes you're like, oh, your answer is 5 plus 3i, that would be a complex number because it has a real and imaginary component. And so we are going to be looking at these square roots and saying, instead of just saying, oh, if I punch in my calculator, it gives me an error, we're going to say, well, just like you can break down radicals, in a similar fashion, we can separate the real from the imaginary factors of a square root and say, all right, well, let's do these. And so if you look at the square root of negative 25, we say, okay, well, let's break it into the real part and then the imaginary part. And so those are factors of the square root of negative 25, and that would be 5 times the square root of negative 1, which we call I. So we will let I represent the square root of negative 1. Okay, just like pi represents 3.14 ... I will represent the square root of negative 1. And so in number 2, we're going to break this up into its real component and its imaginary factor. And then we say, okay, well, the square root of 98, I don't know that, but we can still break it up into factors of radicals that we know times factors that we don't know. And so it would be 7 times the square root of 2. Now, this I part, you tuck it between the coefficient and the radical so that it doesn't go underneath the square root. So you would do 7i square root of 2. You don't do the I after that. You do the I between the factor and the radical. And if it was just 7i, we'd leave it at 7i. But if it's 7i radical 2, it's a little cuter to do it that way. Same with square root of 24. Square root of 4, square root of 6, and then square root of negative 1. That would be 2i square root of 6. That's the answer. So break it up into its factors, and you separate out the real versus the imaginary factors to do this. Now, thinking about PEMDAS, okay, the thing is, this is not equal to the square root of 49, okay, because then your answer would be 7. You have to deal with the imaginary parts and not just pretend they don't exist. And so the answer to this is not equal to 7. That's not true. You can't just multiply those together and kind of gloss over the imaginariness of that, those square roots and pretend they don't exist. What you would do then would be, we can break down each one individually and then place those factors together. So we have to deal with each radical factor as appropriate. So you break down each one, and so that's the square root of 7i and the square root of 7i. Now we can multiply those square roots together. So if we multiply those square root factors together, like the square root here with the square root right here, Okay, then we're going to get the square root of 49, and then times I. Okay, and so what would that make? Well, that would make 7i squared. Now let's talk about this. I is something that can and will be on your answers, but you're not allowed, it's not appropriate to leave I to any power other than just I. Okay, so you may or may not have an I in your answer, but you're not allowed to leave I to any other power on your answer as well. Not okay. And so we've got to say, well, what do we do? And there is a pattern for memorizing like I to the first, I to the second, I to the third, and I to the fourth, and it repeats over and over again. In my opinion, I feel like there's beauty in memorizing fewer things and then just applying the principles that you know, together to figure out what these are. And so I know that I equals the square root of negative 1. And so the question is, what would I squared be? Okay, so if you take I squared, that means you take I, which is square root of negative 1, and you square it. Well, you know from inverses that square and square rooting undo each other. So when you square a square root, you know you get negative 1. And so I squared is equal to negative 1. So those are the two facts I like to hold on to. Okay. There are other repeated things that you can work on. If you Google this, you'll see all sorts of ways to look at this. But to know just two things, I is equal to square root of negative 1. They're interchangeable. I squared, when you see that, because of this square and square rootingness, I squared equals negative 1. Those are the things I like to hold on to. Well, now, in order to apply these, you have to remember a couple rules. Okay. The first rule is that if you have, we're going to go back to reviewing exponents. I'm going to move my paper a little bit and be like, okay, let's talk. So if we have exponents, let's talk about some exponent rules. If you have x to the third times x to the fifth, what do you get? Well, this is x, and there's 5 more. This is x to the 8. Okay, so that's one thing we've got to hold on to. Another thing is if you've got x cubed and this is squared, this makes x to the 6. You multiply those together. Okay, so those are two rules you got to hold on to from Algebra 1. Another thing you've got to hold on to would be if you take negative 1 to an even power. Okay, so to an even power. So let's try this. If you take negative 1 to say like the 4th, what are you going to get? Well, you're going to get positive 1. How come? Well, negative 1 times negative 1 makes 1. And then you've got negative 1. If you have an even grouping of negative things multiplied, it's going to make 1. So if you've got negative 1 to an odd power, what's that going to make? Like negative 1, say, to the 5th. Well, that is going to make negative 1. Why? Well, the groupings make positive 1. Okay. And if you got a negative 1 there, those make 1, and then times by negative 1, it makes negative 1. So negative 1 to an odd power makes a negative 1. Negative 1 to an even power makes positive 1. So those are a couple factors you need to hold on to as we're simplifying some of these imaginary powers or I to higher powers. So let's scooch this up and let's talk about raising I to powers. Well, we have I squared here. And like we spoke earlier, I squared equals negative 1 because of the squaring the square root. And so when you see I squared, you do need to put negative 1 in its place. And 7 times, okay, 7 I squared means 7 times I squared. That gives us negative 7 as the answer to this question. So square root of negative 1 times square root of negative 1 makes the I squared, okay, which is going to be negative 1. The same thing is true on this one here. You cannot just times these and pretend there's nothing imaginary going on here. You have to address each square root that's imaginary and then find the product of their simplified answers. And so when you do that, now if they were real, not square roots of negatives, you could times them and then break it down. But because they're imaginary, you do need to address these. And so you've got the square root of negative 12. So this would be the square root of 12 times the square root of negative 1. And you've got the square root of 15 times the square root of negative 1. So you're going to get a square root of 12 breaks up into 4 and 3. And then an I. And then the square root of 15 doesn't break up. And then you've got another I. And so we get 2. And then 3 times 15 is going to be 45. And you've got an I squared. So dealing with the I squared, that's negative 1. So that brings a negative times the 2. Okay, so that would be negative 2. And then you get a square root of 45, who also keeps breaking down to be 9 and 5. So 3 times 2 is -6. Square root of 5 would be our final answer. So there's a lot of process steps. And if you are a little rusty with your breaking down of radicals, I think the big thing to know is that we're looking to break down radicals using the square root factors that you know. You know the square root of 4, choose 2. Square root of 9, that's 3. Square root of 16, that's 4. The square root of 25, that's 5. Square root of 36, that's 6, 49, etc. And so you want to see if you can break down a radical, one of those factors will divide into it nicely. Okay, and so that's what we're looking to do as well. Now, I to the 7th, that is not acceptable. You may not leave I to the 7th power as your answer. And so when we're trying to break this down, we're going to say, well, what do I know? Okay, I know I squared. Well, I to the 7th does not equal I squared, but we're looking to make groups of I squareds. So I squared is going to be something we know. And if you want to say, let's make that to 7, we'll kind of divide 2 into 7. That goes 3 times. And do you see this would be I to the 6th? And you need another I. Okay, so that would be like I to the 6th and then times another I. That would equal I to the 7th. So you're trying to, in math, you're allowed to substitute in its place. The reason why I'm using I squared and I is because those are the two things that we actually are going to try to substitute in place of, because those are the things we know their values of. Well, I squared equals -1, and -1 cubed, remember how I said if you take -1 to an odd power, it's -1. And if you times that by I, you get -1I or just -I. So we're looking to substitute in the place of I to the 7th equivalent things that we know their values so that we can break that down and not have anything higher than I to the 1th on our answer. So let's look at I to the 38th. Well, if I to the 7th is out of the question, then I to the 38th is right out. And so we're going to say, okay, well, the biggest thing I know the answer is I squared. And so I squared 2 goes into 38 17 times. And so that is exactly equal to it. Okay, if it's even, you're going to be able to represent it in terms of I squareds, groups of I squareds. And so that's -1 is what I squared is to the 17th. Again, -1 to an odd power equals -1. So that's our answer is -1. I to the 13th, well, we start with I squared, and half of 13 is going to be 6. So that gets you to I to the 12th. Okay, so that equals I to the 12th, and we need one more I to the 1. So remember, you add those together. So it'd be I to the 12th, and one more I is I to the 13th. So you need another I. And so I to the 2nd is -1. And so that's -1 times, oh, actually it's +1. I to the 6th, if it's an even power, it's a +1. And then times I, it's going to just be I. And the last one, 424. Well, that's just extra. We've got to say, okay, in groups of I squared, okay, divide 2 into that, you get 2, 1, 2. Okay, it goes in evenly, okay, because it's even. There's no additional I sitting over here trying to round out that answer. So those are exactly equal. You take -1 to the 212. Again, if you take -1 to an even power, the answer is +1. Okay, so that's your answer to this question. So you will want practice on these questions, but this is what the basics of what you do. If you're trying to solve equations, whether by graphing or by solving with the square root property, if you have x squared but no x, you can solve this algebraically by minusing 100 from both sides and saying, okay, well, if x squared is equal to -100, well, it kind of is likened to if you had x squared is equal to 25, you could put plus or minus 5 in for x, and either one would work. So the answer to that question would be x is equal to plus or minus 5. But this is a side note. But this one, if you square root both sides, you can't square root the -100 at all, can you? Now, your answer should be plus or minus, because that's what you do when you're square rooting to solve an equation. So it's plus or minus the square root of -100. Well, what's that? Well, that is equal to the square root of 100 times the square root of -1, or x should equal plus or minus 10i. Kind of weird. So there's no real answers to that problem. However, there's positive 10i as an answer and negative 10i is an answer to that question. So no longer do you write no solution. The proper thing would be no real solution, but there is an imaginary solution to this problem. Okay, so the next one, you minus 100, so you get 5x squared is equal to -100. Divide both sides by 5, you get x squared is equal to -20. Well, again, we're going to have some issues, aren't we? We can't square root negatives, but when we do square root, remember we have to put plus or minus on our final answer, just like here. If you're solving x squared equals 25, both positive and negative 5 will be true. To most quadratics, there are two solutions. And so x is equal to plus or minus whatever the square root of negative 20 is. Well, to be able to break it down, we're looking to break it into its real part and its imaginary part. So this would be square root of 4 times 5 and square root of negative 1. We know the square root of 4 is 2. Square root of 5 we don't. Square root of I, negative 1 is I. And so x would equal both positive and negative 2i square root of 5. So there are two imaginary solutions. One is 2i squared root of 5 and one is negative 2i squared root of 5. So here we go. Next part would be solving equations, finding values that make this true. And this is kind of ugly. I'm not going to lie. Okay, it looks a lot uglier than it actually is. And so if you look at this, you're like, dang it, what is going on? Okay, so from this point, we're saying, okay, this has got to be true, but how? Well, examine it, okay? Do you see that this is kind of a complex number? You're like, well, obviously. Okay, well, complex by definition means that there's a real and imaginary terms within the problem. And so the real ones don't have eyes and the imaginary ones do. So it's not that hard to say, okay, I can tell which ones are real, which ones are imaginary. Well, if this equation is true, well, then that means that this real part has to equal the real part in this problem over here. Okay, if this is a true equation, the real parts have to be equal, and so will the imaginary parts. So the real parts don't have eyes. So to be able to solve this, okay, we would write 6x has to equal 18. Well, divide both sides by 6, x is equal to 3. So if this is a true equation, the real parts must match, and then also so do the imaginary parts. How do you know which ones are matched? They have eyes. Look. So if these two terms have to equal each other, well, we can set them equal and say, okay, well, then that means 12i has to equal 4yi. Say that fast 3 times. Okay, but again, when we're solving an equation, we can divide both sides by I, cancel those out, and you get 12 is equal to 4y. Divide both sides by 4, y is equal to 3. So solving this problem, the values for x and y that have to make it true are not as terrible as it looks. Like, I mean, 13 looks disgusting. But again, use your eyes to say, okay, can I tell which part's real and which part's imaginary? Well, the real parts are the parts that don't have eyes on them. And so this is the real portion of the left side of the equation. And the 13 is the real part of the other one. Okay, and so just set those equal, like a big kid, and we can do this and say, okay, well, then that means that 5x minus 7 equals 13. If you add 7 to both sides, you get 5x equals 20 and x equals 4. And then if you set the imaginary parts equal to each other, then you set this equal to this over here. And again, we can solve it. Divide both sides by I, you get y plus 4, and that's an I, equals 11i. And you get y plus 4 is equal to 11. Subtract from both sides, and y is equal to 7. Okay, so the next thing we're going to do, the next part we're going to be talking about how do you deal with imaginary numbers. And so we want to talk about how do you add them, how do you subtract them, how do you multiply them, how you divide them, etc. So the first one, if you can tell, is adding. And so to add two complex numbers together. So again, a complex number has both a real and imaginary term. And so when we're doing that, we just add the imaginary values together and the real values together. And standard form means you put the real number first and the imaginary number second. So if there's just a real number, you just write the real number. If it's just an imaginary number, you write the imaginary number just by itself. But if it has both of them, you put the real number first and the imaginary number second. So this would give us 7. And then if you put the imaginary numbers together, you get minus 5i. So this is proper form of the complex number 7, subtract 5i. The second question says, hey, let's subtract two complex numbers together. So we would get negative 7 and then plus 7i. And your answer to this, again, put together like terms, combine like terms when you're adding or subtracting. So this 5 and negative 7 would go together. And so the 9 and the 7. And so your answer to this question would be a negative 2 and then plus 16i. And that's the right order. The next one says, hey, let's multiply these together. And so to be able to multiply complex numbers together, we're going to multiply it. There's multiple terms. It's two binomials multiplied together. So you're going to multiply the first by each of the second ones. And you're going to get 15 and then minus 21i. And then you're going to take 2i times both of those. You get plus 10i and then minus 14i squared. We will combine like terms. And remember, you're not allowed to leave I squared or I to any power in any answer. And so remember, if I equals the square root of negative 1, well, then I squared is equal to that squared, which means it's just negative 1. And so if you take negative 1 and negative 14 I squared means negative 14 times I squared. So that's going to be positive 14. And then put the real numbers together and you're going to get 29. Put the imaginary numbers together and you're going to get minus 11i. So that will be our complex answer to this problem. And then the last one, if you multiply these together, you're going to get 72 plus 24i plus 9i, and then again, plus 3, and then I squared. I squared is equal to negative 1, so 3 times negative 1 gives us negative 3. So putting 72 minus 3 together, you get 69, and then that's going to be plus 33i. Okay? When do we use imaginary numbers? Well, you actually use them in electricity. Okay, there's a formula where voltage is equal to the current times the impedance. And so if you multiply the current times the impedance, you're going to get the voltage. And so that's what we're going to do here. There's a problem in your homework where you have to divide them. So just be alert, use the formula as appropriate. You can divide, instead of doing an I, they do a J. And so to multiply these together, you're going to get 21 minus 15j, and then plus 14j, and then minus 10j squared. Again, j squared, j represents I is square root of negative 1. J squared would be negative 1 as well. So that's going to be a positive 10. So 21 and 10 give us 31. So your answer to this question would be the voltage is equal to 31 minus 1j. And you can put a coefficient if you want to, and this would be in volts. Okay, so common application is to multiply those together. Okay, the next question is going to be talking about how do you divide by imaginary numbers. Again, we're not allowed to leave radicals in the denominator, and I is a radical. I is equal to the square root of negative 1. So let's start with a basic question over here. If you've got, say, 7 plus 2i, I'm adding this question to the problems just because I think it's good, over 3i. You know when you're trying to rationalize the denominator, you multiply it by the radical in question. So if you had like 5 over the square root of 2, you would multiply top and bottom by the square root of 2. And that would reduce it. You get 5 square root of 2 over the square root of 4, which would be 5 square root of 2 over square root of 4 is 2. And so that would be your answer to this question. You times top and bottom by the offending radical. Well, if you just have one term in the denominator, the offending radical really is I. So if you times top and bottom by I, again, you're allowed to multiply any fraction by 1. I over I is still 1. It's discussed. It's 1. So you would get 7i plus 2i squared over 3i squared. Well, what is I squared? Well, that's negative 1. So your denominator would be 3 times negative 1 or negative 3. Your numerator would be 2i squared. Well, that's negative 2. And then plus 7i. Now, real and imaginary numbers like to be distinct fractions. So break that up into 2 different fractions. You'd get 2 over negative 3, which is 2/3. And then 7i over negative 3, which would be minus 7 over 3, and then I. So that would be your answer to this question, to rationalize that question. So the next question would be, if you've got multiple terms in the denominator, and you've done this with radicals, is you've got to multiply top and bottom by the conjugate. Maybe you haven't done it in a while, but if you had something like, 5 over 2 plus a square root of 3, how you fix that is you multiply by the conjugate of the denominator, which would be 2 minus the square root of 3. If you multiply conjugates together, they get rid of the offending radical much better than if you, just try to multiply by the radical. So if multiple terms, you use the conjugate of the denominator, and that should make your denominator not irrational. And so if you the conjugate of 3 plus 2i is 3 minus 2i. And if you have multiple terms in the bottom, use the conjugate of the denominator, multiply top and bottom by it. You get 12 minus 8i on the numerator. And on the denominator, you're going to get 9 minus 6i plus 6i. And then 6i. And then minus 4i squared. The middle terms, when you multiply conjugate, will always go away. They're going to be opposites. And then 4i squared, negative 4i squared, I squared is negative 1. And so negative 4 times negative 1 is going to be positive 4. So 9 and 4 makes 13. Again, when you have complex numbers, the real and the imaginary terms want their own fraction. So do 12 out of 13, and then you would do minus 8 over 13, and then put an I there. And so that would be your answer to that first question. And the second one, again, multiple terms, multiply top and bottom by the conjugate of the denominator. And 5 minus I is conjugate is 5 plus I. So multiply top and bottom by the conjugate. You just change the sign in between it. And if you distribute that, you get negative 10i minus 2i squared. I squared is negative 1. So if you multiply negative 2 times negative 1, you get positive 2. So the numerator is going to become 2 minus 10i. Your denominator, multiplying conjugates, you get 25 minus 5i plus 5i minus I squared. I squared is negative 1 minus a negative 1 becomes plus 1. So it's over 26. If you put each fraction over 26 and reduce it, you are going to get 1/13 minus 5/13 I. And so that will be your answer to this question. So that's kind of the solution to these. How do you multiply? How do you add? How do you subtract? There you go.